Hi, here we are again. It's 9 o'clock. We are now looking at the reactivity series. We're going to cover lots of things that you've done before, but a reminder of what's happened in the previous lessons. Just going over some of the reactions that we have seen. So it's all about the reactions. It's about the reactions. We're not really going to see anything from the noble gases because they don't react. So it's going to be the halogens and group ones and other things involved. We're going to look at the different types of reaction, and then from those reactions, we're going to place the elements in the periodic table into an order of the reactivity, which is the most and which is the least, and we call that the reactivity series. So we're going to be able to predict possible reactions based on the reactivity series and where it is in the periodic table. The starter, 5 elements that are commonly used as jewellery. It's just not really linked to anything else other than what do you know for jewellery. 4 metals that you couldn't use as a saucepan. Interesting. No more than 2 from group 1. 3 tests for different gases. You know those. 2 metals that have a higher density than iron but less than gold. And 1 salt, not table salt. Okay? Pause. Let's do those. I'll give you the answers in just a moment. Done? Excellent. 5 metals that are commonly used as jewellery. The most obvious ones are silver and gold. You could also have platinum. That's a very good example. You could have steel, I suppose, because it's not very reactive, it doesn't rust. And sometimes I've also seen brass. Maybe there are others. You can let me know by adding a comment or posting me a letter. 4 metals that you couldn't use as a saucepan. Obviously, if you use group 1 elements as a saucepan, what happens when you put group 1 elements in water? They catch fire, the hydrogen is given off, and so that would be disastrous. So sodium, lithium, potassium, stupid to make as saucepan. Other things that would be really bad to make as a saucepan, I suppose, anything in group 2, magnesium, when you put it near a flame, bursts into flame itself. So you don't want your saucepan to catch fire. So magnesium and calcium would always also be really terrible. And I suppose you could go for some of the other ones like uranium, because it's rubbish. Gold would be quite bad and good in some senses. So gold is not reactive, so it wouldn't rust and it wouldn't react with any of the food you're cooking. But gold is actually really soft. You can bite gold, as in dent it with your teeth. So yeah, you would damage the saucepan. And imagine how rich you'd have to be to have a gold saucepan. What are 3 tests for different gases? I'm meaning things like hydrogen and helium, not farts. So the test for helium, no, not helium, hydrogen. The test for hydrogen is often called the squeaky pot test. You put a lit splint into like a test tube of it, and it goes. That's hydrogen. The test for oxygen is the you take a glowing splint, so your splint was on fire, you blow it out, and you put it into the oxygen. If it relights, that's oxygen. And there's one more, the test for carbon dioxide. If you blow or pass carbon dioxide through lime water, it will turn on lime water cloudy. I've made another video on that. You can pause that and watch that now, from when I was younger. 2 metals that have a higher density than iron but less than gold. When we looked at the noble gases, there was talking about the trend of densities in the noble gases, and you can see that as an atom gets bigger, as there's more things in the nucleus, it becomes generally more dense. And so when it becomes more dense, obviously there's more things in the atom, so it becomes more massive in smaller space. So if you look at your periodic table, if you look at the periodic table and just look at anything higher up than iron, but maybe not so far as gold, you should have a metal that's higher density. And a salt, but not table salt. Table salt was sodium chloride, so pick any other group 1 and any other group 7. Lithium fluoride, potassium bromide, cesium iodide. Excellent. Okay, there's loads of information. You may want to note some of these things down. You may not. Maybe just like listening to my voice. Let's move on. Check. Okay, so going back to the first lesson. The first lesson was the alkali metals. And what happens when you put an alkali metal in water? It fizzes, it zips around, and sometimes it catches fire, and sometimes it explodes. What's happening? The same reaction is happening for all of these things. When you put them in water, some are just happening slightly faster than others. And the general equation is you have a metal, you put it in water, and it turns into a metal hydroxide and hydrogen. How do you know it's hydrogen? Squeaky bot test, yes, well done. Obviously, when it says metal, it's not just any metal, it has to be an alkali metal. That's the general form of the equation. Here is some slightly more specific versions. So lithium and water makes lithium hydroxide and hydrogen. Sodium and water, sodium hydroxide and hydrogen. Potassium and water, potassium hydroxide and hydrogen. Well done. And if you wanted to test yourself on the symbols, there's lithium. How is it different for the other two? All you have to do is cross out Li, both sides, and write in Na for sodium, cross out Na, both sides, and write in K for potassium. Simple. So from this, here's the first stage of kind of making this reactivity. You know what happens when you put these alkali metals in water. You also know what happens when you put gold in water. Not a lot, and copper and silver. So using this information, you can put these metals into order of reactivity. What happens? Does anything happen or not a lot happen? And you end up with this order: potassium and sodium and lithium, magnesium, and copper, silver, and gold. They're all together at the bottom because next to nothing happens in water. Magnesium, if you put it in water, this is gently. Okay, another reaction. Metals and oxygen. What happens when you react a metal with oxygen? Some, like alkali metals, you could just leave them in oxygen and they already react. Others, you might need to burn them to get a reaction to see what happens. There's a little video link at the bottom. Again, another one of me when I was younger and I had less grey hair. But I'm doing some of these reactions. When you burn something like magnesium, it burns it with a bright flame, bright flame, meaning it's burning quite hot. There it is. It makes magnesium oxide. Again, the general equation is the same. If you take a metal and you put it in oxygen, you make a metal oxide. There's the general form of the equation. And you can change it by changing where it just says metal oxide by putting the metal in. Magnesium plus magnesium oxide makes, magnesium plus oxygen makes magnesium oxide. Copper plus oxygen makes copper oxide. And iron plus oxygen makes iron oxide. And if you wanted to balance them, all you do is you change the element. But be careful, some things have different charges. The 2Mg plus O2 goes to 2MgO. Copper and iron, charge on iron is not the same as the charge on copper and magnesium, and the ionic charges. We've done that already, if you haven't. So, based upon that, can we now put these metals in order of reactivity? Well, you know magnesium burns really bright, iron sparkles, if you watch my video, and copper just glows a bit. So magnesium, iron, copper. So now, with those last two experiments, we've got quite a few things we can put in order. Next one, acids. What happens when you put these things into acid? You put copper into acid, almost nothing happens. When I say almost nothing, nothing really happens. Same for lead. Oops. Iron happens. Reaction happens. It rusts, but it takes so long. It's almost painful to watch. I've lost the mouth. There it is. Magnesium. It fizzes. It gives off. Sodium. I wouldn't do that. That's so vigorous. It would probably explode in my face. So I'm not going to do that. But fortunately, I have an animation. You can see. So looking at these, we've got. That's iron in acid, not water. We've got different levels of bubbles and reaction happening. So we can put those in order of reactivity based upon how vigorous those reactions are. Oops. If you, whoa, what happened there? Sorry about that. Jumped all the way to the end. So the general equation, if you put a metal with acid and it is a reaction, this one we can tell there is a reaction because we see bubbles. Bubbles is a sign of a gas being given off, which is a sign of a chemical reaction. If we do the squeaky pop test on it, we know that it is hydrogen. But the general reaction is metal, plus acid makes metal salt plus hydrogen. Metal plus acid makes metal salt and hydrogen. You're going to pause. It's another one, good one to note down. So, for example, the different type of acid will affect the salt that is made. So if the acid is hydrochloric acid, you get a chloride salt. So magnesium plus hydrochloric acid makes magnesium chloride and hydrogen. So hydrochloric acid makes chloride salts. And that's a balancing equation. If it was sulfuric acid, magnesium plus sulfuric acid makes magnesium sulfate. So not the same as chloride, it makes sulfate plus hydrogen. And the last one, magnesium plus nitric acid makes magnesium nitrate plus hydrogen. So if it's a chloride acid, hydrochloric acid, it makes a chloride. If it's a sulfuric acid, it makes a sulfate. And if it's a nitric acid, it makes a nitrate. And again, using the information of how they react with acid, we can put these other metals in an order of reactivity. Magnesium is more reactive than all the others, based on how they react. So put them in order: calcium, magnesium, aluminium, zinc, iron, lead, and copper. And so now we've done an experiment with water, we've done an experiment with oxygen, and we've done an experiment with acid. And from that, we've got an order of reactivity. We know that potassium is much more than lithium and way more than gold. We know magnesium is more reactive than iron and copper. We know calcium is more reactive than aluminium. And if we combine all of these things together, we get the reactivity series of metals. Now, this is a slimmed down reactivity series. You can put more in. So, for example, they've missed out lithium, but we know lithium is less reactive than sodium, but it's more reactive than calcium. And so there are other bits and pieces. They've done this one because there was a good mnemonic to help you remember. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, copper, silver, gold. Please send Charlie's monkeys and zebras in lead cages, securely guarded. Not sure if that's really helpful to remember. Maybe you can come up with your own. If there's anything to write down, it's that, the order of reactivity. We can do that another time. The important thing about the order of reactivity is we can use it to help us work out whether something is going to react or not. If you mix two chemicals together, will they react? Is one more reactive than another? Using the reactivity series, we can work this out. So, for example, if we put gold with acid, there's no reaction. Calcium and water is fizzing. Sodium and oxygen burns vigorously. Silver and oxygen, slow reaction. Okay, so sodium, so looking at the periodic table, sodium's at the top, so it burns vigorously. Let's go down to silver. It's a very slow reaction with oxygen. Where is zinc in relation to sodium and silver? Well, it's in the middle. So you're going to get a middle reaction. So we used that list on the right-hand side in that orange box to work out what happened to zinc. And that makes you a chemist. We can also use it for displacement reactions. We looked at displacement reactions a couple of lessons ago with halogens. If you have a more reactive metal and a compound with a less reactive metal in, and then you throw them together, the more reactive one displaces, kicks out the less reactive. And so you have a displacement reaction. We know that will happen if we look at the reactivity series. If the metal we put in is less reactive, there's no reaction. Let's look at an example. Magnesium plus copper. Okay, so is magnesium more reactive than copper? Yes. So what happens is you get magnesium chloride and then copper. What about silver and magnesium? Is silver more reactive? Silver plus magnesium chloride? No, no reaction. So using the reactivity series, we are able to work out what would happen if we mix these compounds and elements together. If you were to do this, another way that you can tell this reaction has happened is when you mix them together, you often get something forming at the bottom. Here we have like a precipitate, or you can see stuff happening. You can see one thing turning into another. You see a change occurring, color change, fizzing, or something made at the bottom. It shows the reaction is happening. Maybe an activity. You're feeling like you want to do something. You want to copy that table down and put a tick and a cross. Is something going to happen? Is it not? Pause. Do it. Check. Right. For those of you that are lazy and didn't copy the table down, you're just waiting for the answers, here they are. And those of you that did, so proud of you. So proud of you. Okay. You will notice that magnesium is more reactive than all of those, so magnesium displaces everything. Zinc is only more reactive than iron and copper, so it will only displace them. Iron's only more reactive than copper, and copper does nothing. One of the most famous displacement reactions is if you place aluminium with iron oxide. This is the thermite reaction. You have to add quite a lot of heat to kick the reaction in, but once you do, the aluminium steals the oxygen from the iron, leaving this molten iron, and that's how they weld train tracks and other things together. It makes a lot of heat, a lot of quick, a lot. I'll just stop here. It makes a lot of heat very quickly. Now it's time for questions. Okay, so here we have 6 questions. There's more on the next slide. What gas is always produced when a metal reacts with water? Describe how you would test for the gas when calcium reacts with water. Write a word equation for the reaction of calcium with water. Complete and balance the equation for the reaction of calcium with water. You can see the theory. Just fill in the missing number. What gas is produced if the metal reacts with acid? Different question. Write a word equation for the reaction of magnesium with hydrochloric acid. Then, can you turn it into a balanced equation? Number 10. There are just 2 words you have to write down. Don't copy the whole thing out. Just write 10A and then write the 2 missing words. This last one, this penultimate one is tricky. Can you write a half equation to show what happens to magnesium? So a half equation is when you have an atom on one side and an ion on the other side, or you can have an ion then an atom. How it changes from an atom to an ion. So it's about moving electrons. You have to write the element and an E, okay, lowercase e, and then is it oxidation? Is it reduction? Think oil rig. Okay, that's loads. You've worked really hard. Thanks. Love you. Bye.